Relatively soon, some prominent astrobiologists say we'll most likely have either found compelling evidence for extraterrestrial life or banished its possible existence to ever-shrinking edges of the cosmos beyond the rapidly expanding reach of our observations. Such answers could come by the end of the 2030s from any number of initiatives ardently seeking alien life. By then, samples from Mars will have arrived back on Earth, perhaps containing concrete proof that the red planet once harbored organisms or still does today. Spacecraft at Jupiter's Europa and Saturn's Titan will be scouring both moons for signs of life residing in each world's subsurface ocean, or, in the case of Titan, on the surface itself. And advanced telescopes on the ground and in space should be probing the atmospheres of potentially habitable exoplanets around nearby stars, looking for any that shared the same biology-infused cocktail of gases as our own living Earth. Hello everyone, and welcome to another video. Today, we'll be looking at what scientists just detected about advanced alien objects entering the atmosphere. Yeah, you heard it right. So, let's start our video. As confident as astrobiologists may be that their quest will soon bear fruit, however, they are far less certain of how to communicate that success if and when it occurs. How should they go about informing the world that we are truly not alone in this universe, especially given their field's long, troubled history of dubious claims and false alarms? They have been fooled before after all. In an October 2021 article published in Nature, a group of scientists came to grips with a problem. Led by NASA's chief scientist James Green, the researchers proposed a new framework to help verify and then communicate the detection of biosignatures beyond Earth, like the Torino scale for assessing the danger of asteroids. Their idea is to use a scale from level 1 to level 7 that will allow confidence in any given case to be gradually increased. Known as the confidence of life detection, or COLD, scale, it calls initially for simple confirmation that a result is not linked to contamination or some obviously abiotic origin, whereas its final levels would represent robust follow-up observations solidifying a link to life. These things are complex, Green says, but we really need to be able to communicate it simply. There is no shortage of cautionary tales from previous efforts to publicize apparent breakthroughs. In 1996, President Bill Clinton heralded the discovery of a meteorite from Mars, ALH 84001, that appeared to contain signs of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered, he said in a speech at the White House. The finding was not confirmed. Later analysis poured cold water on the tentative evidence of Martian life. Luckily, astrobiology's public positive perception emerged relatively unscathed. Yet, a repeat of that incident could now have disastrous consequences. Today, we have social media, so rumors, innuendo, and purposely false information propagate like wildfire, says former NASA chief historian Stephen Dick. It's all the more reason to communicate effectively. More recently, the supposed detection on Venus of atmospheric phosphine, a possible biosignature gas, had many suggesting a biological origin, but that detection has itself since been called into question. More outlandish ideas, such as the suggestion that the interstellar object Oumuamua found in our solar system in 2017 may have been an alien spacecraft rather than an asteroid or comet, have been met with widespread disdain from scientists and have the potential to dampen confidence in genuine detections of life. The Cole scale could prevent scientists from crying wolf in this manner, Green says, because any overly cavalier claims would not pass the more stringent tests required to progress up the scale. Life detection measurements can be sensationalized, he says. Deciding how to approach actual detections of biosignatures is a topic other scientists have been considering too. In July 2021, scientists met virtually at the Standards of Evidence for Life Detection workshop led by NASA's Network for Life Detection, NFOLD, and Nexus for Exoplanet System Sciences, Nexus, to discuss the idea of establishing a framework much like COLD. Hundreds of scientists took part, with many in favor of more rigorous communication protocols. The potential for us to actually have some sort of interesting life detection event on another world is becoming greater, says the workshop's co-chair Heather Graham of the NASA Goddard Space Flight Center. We want to get ahead of that. If scientists were to adopt the Cole scale, the first of its 7 steps, or levels, would be the actual detection of a potential biosignature. Next, scientists would need to rule out contamination before demonstrating how the signal could be biological in origin. Non-biological sources would then need to be ruled out, followed by an independent additional detection of a similar biosignature. Further observations would need to rule out non-biological ideas before, finally, follow-up observations showed other examples of biological activity in the same environment, making a detection at level 7, essentially proof of alien life. Part of the hope is that the scientist community at large would agree to use such a scale, and agencies such as NASA might also agree to do so, which would also help dictate future missions. If we're stuck at level 4 and we think we can go to level 6 with a mission, I want to fund that, Green says. Ultimately, once use of a scale such as cold became ubiquitous, the reviewers of journal papers could require authors to include it in any claim of biosignature detection. One of the things we discussed at the workshop was how do we incentivize people to use this, says Victoria Meadows of the University of Washington, who was the workshop's other co-chair. The bottom line is that if we don't have such a scale, then people won't use it. The call for such a step-based approach is driven by the unescapable likelihood that any initial detection of alien life is likely to be ambiguous rather than a smoking gun. Any glaringly obvious indication of alien life would have been clear by now, decades into the hunt. So, more subtle searches based on circumstantial evidence are coming to the fore. On October 2021, for example, Zoe Havlana, a PhD student at the New Mexico Institute of Mining and Technology, was a part of NASA's funded team that traveled to cave walls in Italy's Apennine Mountains to collect and study samples of minerals called gypsum, which is sometimes associated with biological activity and may be present on Mars. Gypsum on Mars may be similar to what we're seeing in these cave systems, Havlana says. Elsewhere on Mars, NASA's Perseverance rover is collecting rocky samples to return to Earth in the early 2030s that may contain evidence of life. Its first catch, however, was actually a sniff of the Martian atmosphere. Green says to lease out whether the thin air around the rover contained methane. Previous missions, as well as telescopes on Earth, have found evidence for occasional bursts of the gas suffusing Mars' atmosphere. On our planet, methane is replenished by biological activity, and Perseverance's samples could reveal such activity if the same is true on Mars. Currently on the coal scale, methane on Mars would rank at about a level 4, Green says, but if Perseverance's sample is found to contain not only methane, but methane rich in an isotope called carbon-12, that could change. Life loves carbon-12, Green says. If all the methane in this tube is carbon-12, we just increase our coal level by 1. The next step would be to fly across the surface with a drone like Perseverance's ingenuity, but bigger, to localize the methane to a source that could be directly investigated. Outside of Mars, both Europa and Titan are promising locations to look for life because of their extensive subsurface oceans, and in the case of the latter, a thick atmosphere and the lakes of liquid hydrocarbons. But any evidence found at the two moons is also likely to require careful analysis, and Europa will be studied by NASA's Europa Clipper machine from 2030 and the European Space Agency's Jupiter Icy Moons Explorer JUICE mission in 2031, while Titan will play host to a robotic drone, NASA's Dragonfly, by the mid-2030s. Madeline Garner, a graduate student at the Montana State University, is currently investigating whether an instrument could be designed for robotic spaceflight that could identify the existence of DNA and RNA on these and other alien worlds. Currently, there's no known abiotic source for DNA and RNA, Garner says. Her research into solid-state nanopore technology, now in use on the International Space Station to sequence DNA, could provide a conclusive detection capability for space probes. If we find DNA or RNA, we know that's life, she says. So that's all from today's video. If you enjoyed it, remember to leave a like, subscribe, and ring that bell icon so you never miss our upcoming videos, and don't forget to share your thoughts in the comment section below. Stay tuned, and we'll catch you in the next video.